Okay, so I'll be talking about estimation of low-rank matrices. And in the age of big data and as a statistician, we deal with lots of different kinds of matrices. In high-dimensional inference, we work with large covariance matrices, or its inverse, the so-called precision matrices. Or if you are working with graphs or networks, you need to deal with adjacency matrix. In terms of the structural matrices, we sometimes deal with sparse matrix, banded matrix, Toeplitz matrix, and there's a big class of matrices called the low-rank matrix. And low-rank matrix is of major interest, and mainly because of different kinds of applications. I think the problem was made famous by the Netflix problem, but it's also applied in a wide range of other problems like image compression, facial recognition, and in particular in quantum computing, in quantum state tomography, a major problem is to estimate the density matrix, which is often of low rank. And there are many problems, different aspects of this type of problems, but the goal is almost always the same. We want to develop efficient algorithms to reconstruct matrices from as few number of measurements as possible. And the problem can be formulated in a fairly general way. So we have an unknown low-rank matrix called A we want to recover. But we only get to see some linear transformation of this matrix A, X of A. And this can be equivalent written as in terms of matrix regression. So you have an unknown matrix you want to recover. So you measure the matrix through inner product of a collection of matrices xi. So this inner product is just element-wise vectorized inner product. And there are many different in terms of the linear map itself, in terms of application, sometimes it's given. In statistics, it's also often given, but in engineering, for example, you have the freedom to choose how to design the matrix, the map, linear map X, so that you can recover this matrix A quickly or through small number of measurements. And this A itself is unknown, and sometimes it's exactly low rank, and sometimes it's approximately low rank. And for most of the algorithms, we wish it to do well, even if it's not exactly low rank. And there are also, in terms of this epsilon, sometimes it's noiseless, so epsilon is 0, and sometimes it's noisy. And the goal is try to recover this matrix A from those linear measurements. So for those of you who are familiar with statistics, and this is just a matrix version of linear regression. And in typical linear regression, we deal with vectors. And there's a growing literature on matrix recovery, especially low-rank matrix recovery, and this is by no means exhaustive. So a major question is, how can we design or construct a linear map X, or equivalently those measurement matrices xi, to guarantee exact or stable recovery in the case of noiseless or noisy setting with minimum number of measurements. And the problem has been well studied in the vector case. In the vector case, if we have a sparse signal beta and we want to project by a matrix X or linear regression without noise, then what kind of X will guarantee the exact recovery in the noiseless case? And it's well known that randomness is good. And it's very hard to construct deterministic matrix to guarantee recovery, but it's relatively easy to construct random matrices. It can be random Gaussian, it can be random sparse, or if you are lazy, you can use +1, -1. And life is easy and simple as long as the number of measurements is not too small. So the basic requirement is the number of sample should be of order at least k times log p over k. And in this case, the problem is well understood. And in the matrix case, it has also been studied. And for example, the work by Banrecht and Candice and Plan, they use Gaussian ensemble. So each measurement X is an IID Gaussian matrix. And as long as n, the number of sample, is greater than or equal to some constant c times R is a rank, and P and Q are the dimension of the matrix. And it can be shown that with this number of measurements, you can recover the unknown low rank matrix exactly with high probability. But there's only a small problem. The problem is that we are dealing with matrices, so we need to store all those n measurement matrix for future use. And the matrix is of order p by q, and you need to keep n of them, so you just count the number of entries you need to store up. And for do small calculation, pq say equal to 1,000 and r is 10. And by simulation, this constant c is roughly 4.5. It's not a big constant, but still you need to keep about 45,000 matrices. And that requires 45 gigabytes. And if you further increase the size of the matrix slightly by a factor of 10, so you are trying to recover 10,000 by 10,000 matrix, and rank still keep at 10, now you need this many matrices, and basically you need to cube it. So you multiply by 10. The dimension is multiplied by 10. Now it's 10 to the third, and you multiply together, you need 45 terabytes. And that means that you have series space constraint if you use IID Gaussian matrices. We are all familiar also with matrix compression, which is a much simpler design in the sense that each time you only need to take subsamples of the matrix. And in that case, if we write in this form, xi is simply with one single entry equal to 1, the rest are 0. The problem with matrix compression design is that you are not able to guarantee the recovery of all low-rank matrices. And for example, you will never be able to recover, say, a spiked matrix. A matrix, say, with very few, just say, in the extreme case, one non-zero. The rest are all 0. If you simply sample the entries, then with a high probability that you are not going to be able to see that non-zero one. And you will never be able to infer the value of the non-zero from all other 0 observed values. So what we propose is something different, slightly different from the Gaussian matrix. And we propose to generate Gaussian vectors instead of matrix. So let beta I to be IID Gaussian random vectors of dimension p, and gamma I IID Gaussian vectors of dimension q. So you generate those random vectors, and you measure the matrix A through such a linear operation. So you simply left multiply by beta I transpose and right multiply by gamma I. So in other words, you generate matrices, measurement matrix, by rank 1 operation. So xi is simply beta I gamma I transpose. Now you have many measurements of such a matrix. Imagine that we have a more compact form of writing the measurements. You have n measurements. And for now, let's assume that the measurement error is IID Gaussian. It doesn't have to be Gaussian. Suppose we have such observations. Can we recover the matrix A from x and y? It turns out we can. And we introduce a constrained nuclear norm minimization algorithm. So we define 2 convex sets. The first one is very simple. It's a polytope. So it's an L1 ball. The second one is also a polytope. So this x star is a dual operator of x. And And we form the intersection of the two sets. So intersection of convex sets are still convex. And we introduce a constant called eta. Now, we are going to estimate the unknown low-rank matrix A by constrained nuclear norm minimization. So under the constraint that for any candidate low-rank matrix M, as long as M minus X of M is in that set G, among all those feasible solutions, I want to find the one that minimizes the nuclear norm.
So how does this compare to, so you said it's not going to work for spiky matrices. Now how would that compare to sort of just applying a linear transformation, a random rotation, to the rows and to the columns, and then using single observations?
That depends. When I said that you cannot recover spiked matrix through matrix completion, just sample the entries. So with this, we will guarantee that you will recover the whole matrix. Any low-rank matrix, we don't need any additional constraint. So, and this is obviously a convex program, a convex constraint with convex objective function. So the nuclear norm is just the sum of the singular values. So let's just try one simple example. So let's say we have this grayscale logo of MIT. If you treat this as a matrix, it's a rank 6 matrix. And now suppose that we treat this as a matrix, you left multiply by a Gaussian vector and the right multiply by a Gaussian vector and do it many times and apply the algorithm to recover. And we try 3 different sample sizes. One is n equal to 800. You try n 800 times and apply the algorithm, you recover that. And it's not too bad, but it's not as clean as that one. Now, if you further increase the sample to be 1,000, it's very good. And by the time it's 1,080, you get the original logo back exactly. So it works reasonably well, and we have tried, of course, other examples. But we also want to have some theoretical guarantees. And it can be analyzed, and to show that the estimate A hat, under the condition that n is greater than or equal to some constant times rank times the dimension, the difference between the estimate and the truth under the Frobenius norm is upper bounded by a quantity like that. And the 2 features of this result, one is that we have been assuming that the measurement error Z follows a Gaussian distribution. In particular, if sigma is 0, that means that you have exact measurements without measurement error. Then this side obviously is 0. It means that you will recover the matrix exactly with high probability. Another thing is it depends on the measurement. The recovery accuracy depends on the rank, the sample size, and also the dimension. And those are obvious quantities. But if you only have an upper bound, you're never sure whether there's some other method that will outperform this method much by a significant amount. So we also obtained some lower bound result. And the lower bound result shows that over all possible methods, so A hat, and the chance that the measurement error is greater than this quantity is basically going to 1. So in other words, you can never be much better than this. And you can also write this in terms of, instead of high probability, you can also write this in terms of expectation. And also in both the lower bound and upper bound results, we have a condition on the sample size. And for the sample size, you can also obtain a lower bound to show that that sample size requirement is necessary. If you have sample n, if the number of samples n is less than this quantity, which is the same as here, then no method will work. And this lower bound is a very simple argument. You just count the number of free parameters in low rank matrices. For a rank R matrix, you do SVD, just count how many unconstrained entries. So the number of measurements must satisfy this minimum requirement. And that requirement, by the way, it comes from the simple counting of the free parameters in the rank R matrix, and also the number of samples required in this case is the same as the number of samples required for with Gaussian measurement. And if we compare the two bounds, the lower bound and the upper bound, you'll see that as long as the rank R is not too small, if rank is greater than or equal to log of the dimension, then the method is optimal. And or if n is of this exact order. And we are still not sure what happens if R is very small. And so there's still some room for investigation. And by the way, the requirements on the distribution of beta I and the gamma I can be relaxed. It doesn't have to be Gaussian. For example, you can replace those Gaussian measurements by IID plus 1 minus 1. That's fine. And also you can extend that to sub-Gaussian distributions. We do need some tail conditions on the distribution of the measurement. In some problems, although the low rank matrix is unknown, but we do know they are symmetric. If they are symmetric, it can be further simplified. You don't really need to have different measurement vectors on the two sides. You can just use a single one, beta I. You use beta I on the left and also on the right. And the rest turns out to be basically the same, but I'm not going to go through the details. There's still a small step in this case to deal with some technical issues. But by high level, basically in the symmetric case, you just use the same beta. And you apply exactly the same algorithm and get exactly the same kind of results. And another thing I should mention that the matrix doesn't have to be exactly low rank. If the matrix is well approximated by a rank R matrix, then you have a remainder term. That's the one, A minus max R is a matrix that by removing the first R principal components, what's left. So as long as this term is small, you still have good recovery. And the result turns out to be useful for other problems of interest. And if we apply this result to phase retrieval, and many of you must have heard of phase retrieval, and if you haven't heard of that, that's fine. It's basically when you do linear regression, you take square instead of just the linear term. So in this case, you are still trying to recover the vector, the signal vector theta. And if you measure the signal with Gaussian measurements, so if beta IID Gaussian, then you can apply exactly the same method by using a small trick. So you rewrite the inner product squared to be in this matrix form, then the problem is equivalent to recovering a rank 1 matrix. And then you apply the method and you get a bound. And basically you get this sort of bound for free. And by the way, theta itself is not identifiable because you take absolute value then squared. So you have to match with the best psi. And the problem has been solved before by using different techniques by Emmanuel Candice and Xiaodong Li. And you can see that in terms of the results, that the difference between this and that, the difference is in this minimum. And typically, n is much larger than, this term is very small typically. That means that by using our results, actually you can recover it better. And it can also be applied, I'll be very quick with this one, that it's a standard problem in statistics. You have IID samples, you want to estimate the covariance matrix. And if the covariance matrix is spiked, meaning that it's identity matrix plus a low rank matrix, then you can use PCA to solve the problem. But the question is, what if we only observe the projections of a high-dimensional random vector? It turns out that by applying our method, you can also recover or estimate the covariance matrix only based on rank one-dimensional projections. So I'll skip this one, and because I want to mention a few other problems. And one problem is the so-called structured matrix completion. So you have low rank matrix, and every time you observe, instead of random entries, you observe random rows and random columns. And that problem is related and also is quite interesting to solve. And another problem, and Rob is here, is that you want to estimate the covariance matrix of a data matrix called X, but you don't get to observe this X. You observe a projection of X. So A times X, a sketched version of this, but you still want to estimate the covariance matrix. And there are also other problems like PCA based on projections instead of original sample. And one last problem is covariance matrix estimation based on incomplete data. And I guess I'll just stop here and take some questions. Thank you.
Okay, let's thank Tony. Maybe David Woodruff could already come up slowly and set up. Any question to Tony?
Rob?
Go ahead. So if I have full Gaussian sampling measurement matrices, do you think that it could be possible to compute with sufficient statistics with lower storage?
I don't think so. I don't know for sure, but I don't think so.
Maybe still.
Yeah, I was curious about that last comment about missing data. What kind of model did you have in mind? And
You have a data matrix X, then you want to estimate covariance matrix. Now you don't have the full matrix. You only have a value, so say they're missing at random. So you don't get to see all those entries.
So you see certain entries of the sample covariance?
Exactly. It's like it's like matrix completion, but you are not trying to complete the original matrix. You want to estimate the covariance matrix.
Okay, maybe one more bit.
Three operations like distribution or compression. Remember the bunch sparsity?
Uh-huh.
So can you push your result to that case too? Because you might lose too much information if you do two.
Because in our setting, we only generate random vectors. I think it's possible to extend that +1 minus design to also sparse. Yeah.
Okay, let's thank Tony again. Thank you.